Good evening. Can you hear me?
Good evening.
Good evening, sir.
Good evening. So my voice is audible?
Yes, sir.
Yes.
Let us continue our discussion. So I have just got your copies for both the subjects, gas turbine and CMTFE late, quite late. So now I will check and maybe next week I can show you. I don't know how to show the copies here. Means what is the way? Means one by one I cannot show. Then it will take a lot of time. Let me see. And I am not putting marks also on the soft copies. I am putting marks on a separate Excel sheet. So we'll see what to do. Maybe I can discuss the results and you can see your copy. We'll see later next week. So let us continue our previous discussion. In the previous class, we had started discussing about the second method for discretization, which is finite volume method. Previously, we had discussed finite difference method, and we noted a few advantages and disadvantages of finite difference method. The main advantage is that it is quite easy to derive the finite the discretization equations based on the finite difference method, because you know how to tackle all the derivatives. Any type of derivative is present, you know that you can use some sort of combination of Taylor series expansion to find out the algebraic equation for that derivative. Okay, so that is one major advantage of finite difference method, which means that you can just hold for a second. Sorry. Okay, I'm back. So, which means that we can tackle complex physics, okay, using finite difference method if the geometry is simple. So there can be two types of complication in a CFD problem. The geometry can be very complex, or the geometry can be simple. Complex geometry means, say you are designing for a complex casting which has very intricate details, okay, or some sort of flow channel with very intricate details. But the physics may be very simple. Say normal flow is occurring, not much chemical reaction or any other things are there. On the other hand, we can have a very simple geometry but very complex physics. Means geometry is like a pipe or a rectangular domain or just a square box, cubic box. But there is chemical reaction, multiple chemical reactions are occurring. Some diffusion process is going on. Okay, some heat generation source is there. Maybe some electromagnetic forces are acting. So the physics may be difficult. So in the second case, where the geometry is simple and physics is complicated, finite difference method is very useful because you can quickly develop the discretized equation. You can also use finite volume method, but like even finite difference method is quite suitable in that case. But when you go to complex geometries, as we had discussed previously, then there is a major drawback of finite difference method because it cannot tackle complicated boundaries, irregular boundaries easily. Okay, it can tackle by some sort of interpolation. So you have to take a larger domain as compared to this domain. I don't know whether I have that. Okay, so I have it still. So you have to take a larger domain around the actual and then modify the governing equations so that you put something outside the domain also, say some properties with conductivity 0 or something like that, viscosity infinite, so that no flow can, and then solve over the entire squared domain and then find out the values inside the irregular domain. Okay, this is the sort of thing which can be done for simple case, means like using finite difference method for complicated geometries also. But what is the main drawback of this? The calculation at the interface are not very accurate. If you want to calculate, say for example, there are a lot of interfacial properties, right? For example, shear stress at the interface or heat flux at the interface. This type of calculation will not be accurate because you are not accurately capturing the interface. Your interface is like a staircase in this case. Whereas using finite volume, you can put any arbitrary control volume near the interface. I can put very small control volumes near the interface with arbitrary shape so that they can, like arbitrary triangles, so that they can almost path of the boundary. I will not put curved interface, but we can put small triangles so that it almost follows the path of the boundary. And as a result, we can very accurately capture the phenomena such as like phenomena which is very important at the interface, such as say for example viscous flow effects, boundary layer effects, shear stress, then heat transfer at the boundary, things like that are much more accurately captured using control volume method. Okay. The other important difference, although it is not apparent from the equations, but the way the finite volume method is done, you take a control volume. For finite difference method, we only had some points, okay, no volume around the points, and we only had values at those points, and calculated our equations or derived our discretized equations based on those in a regular fashion, like going from I is equal to 1 to some value, j is equal to 1 to. In finite volume method, we have a volume around a grid point, okay, or a volume in which there is a representative equation, and we integrate all the equations over this control volume. And because of this nature of this derivation, all the properties such as say heat flux, mass flux, then momentum, these are conserved over each control volume and over the entire domain, as a result over the entire domain. Okay. So this is a very important property of finite volume, and this property is valid even if the number of grid points or control volumes is very low. Say if I divide the domain into only 4 controls, then also the conservation will be there. Okay, there we don't have to check for conservation. The mass, momentum, all these things will be conserved over the entire domain. Whereas for finite difference method, there is no guarantee that overall conservation will be there. We can only guarantee at any point the conservation will be there. Means because we are taking the differential form of the equation, at any particular point the conservation of mass momentum will be there. But if you sum up over the entire domain, there is no guarantee that mass momentum things like that will be conserved. Okay, that is one important difference. These things we have discussed in details, but I am still going because sometimes people get confused. They cannot summarize in a very neat manner. So I was trying to give a very neat summary of what is the difference, what is the advantage and disadvantage of both these methods, because this may be asked in the interviews for you guys. It's a very important. Similarly, there is another method which is the finite element method, which we have not discussed much because it's not used much in CFD process, because it's much slower as compared to finite difference and finite element method is also a method of discretization, which is generally used more for structural problems, as you guys know. And where actually there are also control volumes which are called as and grid points which are called as nodes, but each element might have multiple nodes, and some sort of functions are used to represent the properties within the elements, and then using minimization of energy or like variational method, you solve equations. Okay, so we'll not go into the details. And then what we have done, we have taken a very simple case. Okay, first we have seen how the general case works out. Means if you have a convection diffusion problem without any source term and without any transient term, how the equation gets converted while integrating from a volume integral to a surface integral. Okay, the physical significance. What was the physical significance of this? The physical significance of this was that of this conversion is that whatever is the change in the volume occurs only due to whatever flux comes in from the boundaries. Okay, that is what is shown here. Okay, whatever is the change that is occurring for any parameter in the volume, say for parameter phi, if phi is temperature, the change in energy in the volume is because of energy coming in from the boundaries, all the boundaries, like total boundary. So those are balanced. So this is actually given by the divergence. And for simple cases, what can be done if you don't have arbitrary geometry? If you have, like say for example, this pentagon. Okay, if this is a control volume, you can find out the flux over each individual phase, as we will see, and then just add those things to find out the surface integral. Finding the surface integral is not difficult. Okay, you can find out the flux over each of the phase. Okay. So most of the course we will just tackle regular geometry like a rectangle or square will be there, and there will be 4 faces in 2D and 6 faces in 3D, 2 faces in 1D. Okay, and the flux can be very easily calculated. Means because the velocity is aligned, velocity vectors are aligned with the normal direction of the face. Directly you can calculate. But if the velocity vectors are not aligned with the normal direction of the face, you have to take the dot product. Okay, to find out the values. So after that, what we have discussed, I am again repeating this because it's very important, this area. Okay. So after that, what we have discussed is that something called a profile assumption needs to be taken. Otherwise, we cannot proceed. Once we have converted this volume integral into a surface integral, then to proceed further. Okay. So after converting to surface integral, what we will have, you some terms which gives us the flux over the interfaces. Because you remember what what I said just now. Okay, you need to calculate the flux over all the faces. So we need the flux over each of the faces. And to find the flux at each of the faces, we need some sort of profile, means some sort of variation of the concerned variable. Like for example, in this case, if the concerned variable is relevant variable is temperature, how this temperature is varying with distance x from one control volume grid point to another control volume grid point. Without that, we cannot calculate the flux. Okay, we need some assumption. Why do we need this assumption? Because remember, each control volume is represented by a single grid point, and we assume that the variable value is only present at the grid point. We do not assume anything in between the grid points. We do not know what is happening. Say here at point P, the temperature T is 100 degrees centigrade, and at E the temperature is 120 degrees centigrade. That is the only information we know. We don't know whether from 100 to 120 degree the change is occurring linearly, or it is 100 up to this interface and sudden jump occurs and then it is 120, or say it goes to 90 and then again increases to 120. We do not know this. The only information we have in a CFD problem, in a finite volume case, is the variable values at the grid points. So now we need to assume some sort of function between the grid points so that we can calculate these derivatives to find the flux at the interface. Okay, and we were discussing this point with an example. I will reduce the size. Okay, I am using a big monitor, so for me it is looking large, but for you guys it may look slightly smaller. I would suggest everyone to use laptop if possible instead of mobiles. So laptops or some monitors connected to laptops if it is feasible. So we have taken a very simple example, a 1D steady state heat conduction with heat source, and tried to derive the. So this is our example for the next few classes. Okay. Then we will later on add the convective term. How to add the convective term? And before that we will add the transient term. But let us first consider this is just a representative equation. Although we are writing in terms of temperature, same thing can be written in terms of composition like chemical composition or any other variable. Means we can write this as d dx of gamma d phi dx plus some source term. Okay, this is the general diffusion source term equation. Diffusion with source term. Okay, where there is a flux. Here the flux is heat flux, but it could have been mass flux or some other flux. And we have seen how to derive the discretized equation. What were the steps again? Let me just repeat again. So if we divide the first step is always to divide the geometry into certain number of control volumes. Okay, so here we are assuming that there is a long 1D rod and we are dividing into 6 numbers of internal control volumes, 2, 3, 4, 5, 6. 2 grid points are there at the ends and 6 internal control volumes. Okay, each control volume is represented by a grid point at its center. So for any particular grid point like 4 or 5, we have taken a close-up view. Okay, while this grid point 5 is denoted by P, this is the normal notation used in many books. The east neighbor, which is the 0.6 here, is denoted by E, and the west neighbor, which is the 0.4 here, is denoted by W. Okay, why is it is like this? Because we can just keep on repeating the same calculation again and again by moving from one direction to other. Say we have calculated with 5 as P. Okay, once we have already done discretize the equation, we will go to 0.6, and now 6 will become P, and 7 will become E, and 5 will become W. Okay, so ultimately we will just keep on repeating the steps for each of the internal grid points. Okay, boundaries are treated because if you want to take grid point 2, automatically some value will be known here, and that will come into picture, which we will come to later in the next class. But that is the idea, and with this we have denoted some other notations also. That the control volume, what is the control volume here? For 5, it is going from this boundary to this boundary. So from west, small w, to east, and the length of the control volume is delta x, because it's a 1D problem, it only has one length, delta x. If it was 2D, it will be delta x into delta y. And the distance between the grid points in the west direction is delta xw, and in the east direction is delta xc. Okay, this is our geometrical notation. This can be used even in the computer programming, but instead of pw, you might write I plus 1 and I minus, and for the boundary you might write I plus half and I minus half. Okay. So integrating this equation, we had obtained some equation, and we used some profile assumption for that. We have seen one profile assumption that can be used is that in any control volume, the variable temperature is constant. Okay, so piecewise temperature in each control volume. What was the problem with that? Any reply from the students? Please ask a few questions or give some answers. Otherwise, I don't know whether you can hear me or not, because I'm not looking at the chat. Can you hear me still?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So why could not we take this piecewise constant profile? New students, MTech students, old students already know. Yeah,
Discontinuity, sir, due to discontinuity.
there is discontinuity. Okay, there is discontinuity. Directly temperature itself is discontinuous, so derivative cannot be calculated. Okay, it does not exist. Second profile assumption we have taken was, okay, let us not have the discontinuity at the interface. So what we have assumed that in a control volume there is linear variation. Second control volume there is linear variation. Third control volume there is linear variation. In such a way, so the temperature is equal to the temperature of the grid point at the center, because that has to be true, because that is the only known value, TW at center, TP at center, TE at center. Okay, but the lines have such a slope that this line matches with the temperature at this point matches with the temperature of the next grid point. Okay, so there is no discontinuity in the temperature, but now there is a discontinuity in the slope. Although temperature is continuous, slope is discontinuous. And again the same problem is there, that if the conductivity is same on both the control volume, k dt dx is different, which cannot be true in a physical situation, because heat flux from one boundary has to go to the other boundary, right? Means has to go to the other control volume. So there are no separate heat flux values for two control volumes. This is a very important point. Okay, sometimes you get confused when you are calculating the things for, say, the pth control volume. Say this equation, let me keep it here open. You are doing all the calculation for the pth control volume. Okay, you have one heat flux at the east side of pth control volume and one heat flux at the west side of pth control volume. Okay, west face, east face and west face. So you are calculating, when you calculate these heat fluxes at the east and west side, you can easily calculate now, because you know what is the, because you have the profile assumption that the temperature is linearly varying like this. Okay, so you know the slope for the pth control volume, you know the slope at this point from the left direction. Okay, for the pth control volume, it is from the left direction. So you will be able to calculate k dt dx at east for the pth control volume, and similarly at west for the pth control volume, and we will get some equation. Once you go to the next grid point, and this E becomes the P, means for the next grid point this will become the P. Then again, based on this new slope, you will again calculate the heat flux at this point and at this point, and you will be able to do the calculation again. Means this will now become the west point for this grid point. This will become the west point, and you will be able to calculate k dt dx for this point. The problem is that the heat flux that you had calculated for the pth control volume at this side will not match with the heat flux that you calculate for the next control volume on this side. Okay, but actually they should have been equal. Okay, there is inconsistency. This is not consistent. So that's why we have rejected this. Okay. It is not that we cannot calculate. We can calculate, but it is not physically realistic. That's why we have rejected this. Okay. The third assumption that we had taken in the previous class was a piecewise linear interpolation between each grid point. This is also piecewise linear. This is within the control volume, but now instead of control volume, the linearity is between one grid point and adjacent grid point. Okay. So for example, the control volume is between small w and small e, but the temperature is varying linearly from the grid point P, means the center part of the control volume, to the center part of the next control volume in a linear. Similarly, the temperature is varying from the central part of this control volume to the center part of the previous control volume in a linear fashion. So it is piecewise linear between each grid point set. However, it is not linear. Okay, or the slope is changing within a control volume. So within a control volume, it is actually not physical, but because we don't do any calculation within the control volume, means we are not going to calculate any flux at the center, so there is no issue. So actually it is in a control volume, it looks like this, it goes up and goes down. Okay, but it does not matter to us because these assumptions are only taken for calculating the flux at the interface and for nothing else. Okay, so ultimately whatever profile assumption you take, given a very fine grid distribution, your results will all tend towards the correct result. Okay. However, if it is a very coarse grid, the results may vary. Okay. So that may play a role. So then with this profile assumption, what we have done, we have calculated the derivatives dt dx and dt dx at east and west, and we found we have written in this form in the previous class. APTP is equal to AT plus AWTW plus B. This is a very standard form of equation you will find in many like say Patankar's book, then Malala Sekara. Okay. So what it means that for any grid point denoted by P here, or you can denote by I, it is given in terms of the temperature, or for this grid point is given in terms of its neighboring temperatures. See, in this case, there are two neighboring values, east side and west side. If there are more neighboring values, if it is a two-dimensional problem, there will be four neighboring values. So it will be in terms of the four neighboring. In general, APTP is summation of all the neighboring values, A, NB, TNB, where these A values are the coefficients, and these coefficients are known values. These are based on the conductivity at the interface and geometrical parameters. Okay. You can ask how we know conductivity and geometrical parameters. So conductivity we will see today, how to calculate at the interface. But remember, we know the material properties, so at least we know the conductivity at each grid point. Okay. So we know the conductivity at each grid point. Based on those conductivities, we need to find the conductivity, some equivalent conductivity at the interface. Okay. But for each grid point, the conductivity is already given as an initial input to your problem, because you are assuming that, say, this is aluminum or something like steel, or say up to P, this is aluminum, from P, accordingly conductivity also can change. What about the geometrical parameters, delta XC, delta XW, all these things? These are generated while you are generating the mesh. In CFD software, you see a very nice looking mesh. That is just a visual representation. Okay. Actually, inside the software, what they are doing is they are actually just noting, they are dividing the domain into a certain set of control volume, putting one index for each control volume, like 1, 2, 3, 4, 5, 6, like a name for each in terms of number, and then associating certain geometrical parameters for each control volume, like what is the starting point of that control volume, what is the ending point of that control volume, things like that. What is the center of that control volume? Okay, these things are, so generally it is stored in terms of vertex. So each, so for example, here the control volume has two vertex, small w and small e. So in terms of this vertex, if I store the vertex values, I can always calculate what is the grid point location, because it will be the centroid. So it will be halfway between the vertex. Okay. If we take a look at a more complicated geometry like this, like you will use in a normal CFD software, this is a pentagonal control volume, right? So in this case, what will be summation A and B, T and B? It will have 5 neighbors. Okay, neighbors are all the control volumes which have a face common. Okay, not vertex common, common face. Okay, for example, this is not a neighbor. I hope you can see my cursor, and I hope there is no lag. Okay, I am pointing at the triangle. This triangle is not a neighbor because it only has a common vertex, no common face. However, this quadrilateral is a neighbor because it has a common face. So this coefficient and temperature of this will come into the discretized equation of this. Similarly, this is a neighbor. This is not a neighbor. This is a neighbor. This is not a neighbor. This is a not a neighbor. Neighbor. So 5 neighbors are there because there are 5 faces. Vertices are not. Vertices are not. Common vertices do not mean neighbors. Okay. So the discretized equation for this will have APTP is equal to A1 T1 A2 T2 A3 T8 T4 A5 T5. Okay. All of them are unknown. So simultaneously we will have say n number of equations and n number of, because we will develop equations for each grid point. So we'll have n equation, n unknowns, and we can solve it to find the temperature values, which we'll see later. Okay. So I have digressed. I was trying to show something here and I have forgotten what I was trying to show. Okay, now I remember. So what your CFD software is doing when it is meshing, it is showing you a nice mesh, but actually it is not storing any of the lines and other things. It is just storing, it is creating a number of control volume, means it is generating what are the index of the control volume. So this is 1, 2, 3, 4, 5, 6, 7, 8, even if it is irregular, so 9, 10 like this. And for each of the control volume, what is the coordinates of the vertex? So for example, if this is the 11th control volume, what are the coordinates of its vertex? Okay, it is storing that, and based on that it can easily find the centroid. Okay, and any other properties like what is the slope of each of this face, what is normal to each of this place. All this can be calculated if you know the coordinates of the vertex. So that is what a meshing software does. So my point in discussing this was that once you can generate an equation of this form, APTP equal to AT plus AW TW plus B, all these delta X, delta XE, delta XW values will be known after meshing, after you generate the mesh or grid. Conductivities can be calculated at the interface based on grid point conductivity. Grid point conductivity, because it is initially given as material property. Source term is also a given property, like we know what is the heat source, or we have to derive what is the heat source or any other source is there. Say for example, heat is generated due to friction. We know how much friction is occurring. We'll put some equation for friction, say based on some velocity or something else, and like that. Okay. So S into delta X is also known, so B is also known. So only unknowns are TP, TE, and TW. Okay, one equation, 3 unknowns. But if you derive the equations for all the, you will have number of equations which are equal to the number of unknowns. So going back to our problem here, we will derive equations for these 6 control volumes. 6 unknowns and 6 equations will be there. Remember the boundary, from the boundary condition we have some additional info. So T1 or T8 will be known, or some relation of T1 and T2 will already be given. Okay, so only 6 unknowns will be there and 6 equations will be there, which can be simultaneously to find out the values. Okay, so any equation, even if it is a complex geometry, not a regular geometry, very irregular geometry, ultimately is written in this form: APTP equal to summation A and B T and B plus B, where all the A values, coefficient values are calculated based on geometrical parameters and input parameters. Okay, and source term is also calculated based on geometrical input parameter. So we have seen a few cases, and we have seen what can be a suitable profile assumption, okay, for calculating the flux at the interface. Let us consider try to formulate a more accurate profile assumption. Okay, we are thinking, okay, linear profile assumption. Let us go for a more accurate assumption, a quadratic profile assumption. Okay, so why we are assuming that it is more accurate? Because now we will calculate the profile for each grid point, not based on, or for each interface we will calculate the profile. Here we were calculating the profile at the derivative at each interface based on two grid points, but with quad the curve is denoted by three grid points. Okay, so let us try to see what happens in that case. You can still hear me, right, students?
Yes, sir.
Yes, sir.
Okay. Again, I will say that these are all common for the dual degree students who have done the CFD elective with me, but these are part of the syllabus for CMTFE also. You know, it's almost similar syllabus is there. It's just a revision for you guys. Okay. Both the courses are structured in somewhat similar manner, but with more tutorial component for this. So I will give you some assignments. I have to formulate some assignments, and we'll start doing some tutorials after a few classes. For some reason, it feels that the number of classes are less in this semester as compared to regular semesters. We have to see. Let us come back to this. Okay. So say we want to assume a profile for this control volume W. Okay, control volume W. Okay. If we take a quadratic profile, we will take the neighboring grid point values, and based on these 3 points, we can join the line. It will be a quadratic equation, and you can join the join 3 points with a line. It's a quadratic curve, basically. Okay, like a parabola. So you can join these 3 points with a line like this. Okay. Now once you go to the next grid point P, okay, next control volume P, which is going from small w to small. For this, you will also assume another profile. For these cases, you have to take the grid points which are adjacent to P. So for this case, I have to take the grid points W, and this is east. Okay, wrongly written as W. This is east. I have wrongly. Please note this. Okay, that this is east. So now what is the issue with this? When you are calculating this flux at the interface small w, when you are doing the calculation for the control volume P, like we have seen here, okay, we are doing the calculation for the control volume P. We are calculating the flux at east face and west face, k dt dx east and k dt dx west. How will you calculate the k dt dx west for the control? Based on the rate curve, I will calculate the k dt dx. So I can calculate what is dt dx based on the slope of the rate curve at the point small w, because that is the interface, and I will get some value of dt dx, and it's fine. I can calculate what is k dt dx west. Similarly, I can calculate what is k dt dx based on the same red line. So up to this point, there is no issue. We will derive and we will get APTP is equal to AET plus AWTW plus B. Okay, some equation. Now, once you try to derive for the previous or for the next control volume, say we are going from this side to this is the next control volume, and for this control the profile assumption is again quadratic, but now it is based on the neighboring values of W control volume. What are its neighbor? Let us denote them by W on the east side, on the west side, and obviously it is P on the east side. So typical notation is WW and this is EE. Okay, so it is WW on the west side and P on the east side for this. And if you join these 2 points, you are getting a different curve. Obviously, for this control volume going from this line, this dash line, this dash pink line to the next dash pink line. This is the control volume, right? So for this control volume, this is the curve, this blue line. So when you are calculating, again you will go through this type of calculation. For this W control volume, the K dt dx at east you have to calculate, and you can easily calculate based on the slope of the blue line. Okay. Now issue is that the heat flux that you are calculating for this interface based on the slope of the blue line may not match with the heat flux that you have calculated for the other control volume based on the slope of the red line. They will only match if the slope of the red line and the slope of the blue line are same or equal at the interface W. Otherwise, we will have 2 heat flux values, one for the W control volume and one for the P control volume. And again, the same problem will be there, means it is physically inconsistent. It is unrealistic. So the main point here is to show that it is not always that you can take higher order terms or higher order profile assumptions to get better accuracy. In this case, we are seeing that by taking a more complex curve, by incorporating more points into the curve, we are actually getting inconsistent result, incorrect result. Okay, it is not possible to get the. So in many cases, it will still give the correct result. In what case it will give the correct result? So it is seen that it gives the correct result when the small w, the interface is midway between, like all these control volumes are of same length, and the interfaces are midway between the grid points. Okay, in that case, fortunately, the slope of this red line and blue lines become equal. Okay, although it goes like this and it goes like this, the slope becomes so. Fortunately, in that case, it is physically consistent. But in other case, when we have different size control volumes, the slope will be different and you will get error. So that is, so we have to be very careful about the profile assumption. Okay, you cannot arbitrarily take the profile assumption, but it does not mean that what is the main difficulty in this profile assumption. Main difficulty is that you do not know the solution, right? You do not know how the variation is there. Here I am drawing something based on TWW, TW, TP, TW, T east. But this is only arbitrarily I am drawing. I don't know what is actual values. It could have been here. Without knowing any information about the temperature, we have to take the profile assumption. Okay, that is the difficulty. But we have seen that whatever is the temperature profile, taking a linear approximation between the grid points generally gives physically consistent solution. Okay, because of the nature of the profile assumption, the heat flux will always be equal on both sides, because you are taking the common for both the grid points, for both the control volumes for calculating the heat flux. Okay, so that is the best profile assumption in this case. Okay. Any questions on this very important thing? Okay.
No, sir.
Okay, good. So these points are written here. I am not reading this. You can. This is just written whatever I have discussed, so that you can read later, okay, in more details. So what I meant is
So,
the DTDX. Yes, tell me.
nothing, sir. Nothing, sir.
Okay, so it means that DTDX may not be equal at the small CBW or CBP. Okay, only equal if small w is midpoint between W and P. Okay, hence the results will be unphysical as flux balance is not satisfied at the interface. And our conclusion is that higher order function may not give better results. So it is better to stick with what is known. We know that this type of profile assumption is suitable. Okay. Now we will go into the next few minor topics. Okay. we have seen how to discretize using control finite volume method for a simple, but some of the things are still left like I have not declared or discussed how to take those values like conductivity, things like that. Okay, we have assumed that K is known, KW is known at the, but how actually these are treated or how the source term is treated, that we have discussed in more details. Okay, one very important thing that was there present, but you might not have, because I have not elaborated deliberately. I have not elaborated. You might not have say absorbed that, is that we are taking different profile assumptions for different parameters. For example, the profile assumption for this calculating the flux at the interface has been taken as linear, but for the source term, the profile assumption is that the source is constant for each control volume. Means from small w to small e it is constant. Next, from small e to next boundary it is another value. Okay, so source term is piecewise constant in each control volume. That's why we have written it like this. Just hold for a second. Okay, some call is coming. Can you hear me? Hello.
Yes, sir. Yes,
Oh,
sir.
yes, sir.
Yes, sir.
Okay.
Yes, sir.
So
Yes, sir. Yes, sir.
one thing which might not have been apparent, yeah, one thing which might not have been apparent was that we had taken different profile assumption. For the temperature, for calculating the flux, we had taken linear, but for the source term, we had taken constant profile in each control volume. That's why we have written it like this, S into delta X. Otherwise, we could not have written. If it was some other variation, we had to take the neighboring, like how it is varying within the domain. All these things we could have, because we have assumed constant, we could write it like this. Okay. So what I mean to say is that different profile assumptions can be taken for different parameters, such as I can take linear profile assumption for T, constant for S. I could have taken linear for S also. We have to see whatever profile assumptions we take, whether it is physically consistent or not, means whether it violates any physical principle or it does not violate any physical principle. For example, we have seen that if we take quadratic or stepwise function for T, it violates the physical principle that flux should be consistent at the interface. Flux cannot change at the interface. So similarly, we have to check for conservation fluxes, things like that. Okay. Second point is that if K or source term, etc., which were part of this equation, okay, K and source term are part of the equation. Part of the equation means in the form of coefficients. Is this terms are function of T, coefficients itself become function of T. Okay, AP, AE, AW, B, this will become function of T. So if AP, AE, AW becomes function of, okay, then equation becomes non-linear and some iterative process is required for solving them. Okay, directly you can solve. So what you have to do is some question. Please switch off your mic, otherwise somebody's mic is on. And so if the coefficients become function of, you have to use some iterative method. What will be the iterative method? For example, you know the previous iteration value. Using that, you can calculate the coefficients based on the previous iteration value of T. So say it is T old. Now once you know the coefficients, you calculate new values of from this equation by solving for all the equations together. And these new values of t you again use in the next iteration to find the coefficient. And again solve to get new values of t. Like this, some sort of iteration has to be built up. Okay, so this is how nonlinearity is tackled. It is not difficult to tackle. It is just more complex, means in terms of coding and in terms of simulation time. Okay, so this is how we discretize formulate a discretized equation using finite volume method. Now, before going into the conductivity and source term treatment, we need to discuss about two important conditions or two important requirements of discretization. Okay, discretization cannot be arbitrary, and we have already discussed this without formally saying about them. We have already discussed this, but now we will formally define these parameters requirements. So one is that any discretization scheme that we should be physically consistent. I will come to the meaning of what physical consistency means, but it should be physically consistent. For example, physically consistent means we have seen a case that flux should be physically consistent. Similarly, there are other issues with physical consistency. Okay, so physically it has to give realistic result. It cannot give unrealistic result. It can give inaccurate results. Unrealistic and inaccurate are two different things. Okay, that you have to be very clear about. Things can be unreal, things can be realistic but still inaccurate. Means there may be 20% error, even 50% error may be there, but still it may be realistic. Okay, means the physical pattern is, say, if we know that the temperature should increase, if we put a metal sphere in a furnace, the temperature should increase. And if the temperature in the experiment, the temperature increases in 1 to 900 degrees centigrade, but our model gives us that the temperature increases to 500 degrees centigrade instead of 900 degrees centigrade. That is still physically consistent because we are getting that temperature is still increasing, but it's very, instead of going from 30 degree to 900 degree, we are going from 30 degree to 500 degree. It's very inaccurate but physically consistent. But if our model gives us that the temperature becomes minus 20 degree after calculation, it is physically not consistent, because with a positive heat source, temperature cannot go down, temperature has to go up. Okay, so both the things are different. Accuracy is different and physical consistency is different. That we have to be careful about. So any discretization scheme has to be physically consistent, although it can be inaccurate. Okay, accuracy depends on many other factors. Means what is the number of grid points, control volumes. If we keep on increasing the number of control volumes, accuracy will increase. But even if we are very coarse, like say we are dividing the rod that you had seen in the previous example. So this 1D rod, if I divide it into two, still the solution should be physically consistent. Okay, if the temperature needs to increase, it should increase even with two control volumes. Okay, it cannot be decreased. So this is the thing. Okay, but obviously if we have less number of control volumes, it will become more. Second is that overall balance has to be there. Overall mass, momentum, energy has to be conserved, and that second part is always already taken care of by the finite volume formulation. Okay, but these are the two important requirements of discretization. So physical consistency, I have already explained what it means with one example. Let us take a look at another example. Okay, it means that solution has to be physically realistic. Okay, what we know from physics. For example, say there is a 1D conduction problem without any source term. So there is a that is kept at 0 degree centigrade at one point and 100 degree centigrade at another point. Okay, initial temperature is say something say 30 degrees.
Sir,
Yes, tell me.
sir, then what is
Yes, tell
stable
me.
meaning? What is solution is stable meaning? What's consistent meaning? If it is should give a realistic result. If consistent
No,
means
no,
that.
no. Those are other. Yes, good point. Stability is a different thing. Stability is a different.
Stability
Consistency
is related
is
with
different thing.
errors.
Okay, I will explain. Yes, yes. We have briefly discussed also before the. Who are you? Who is asking the question?
Suman, sir.
Okay. See, physical consistency means that the solution, as I will describe, has to be realistic. Stability means that error should not increase from one iteration to the next iteration. Okay, error should
Okay.
decrease from one iteration to the next iteration. So what will happen? Let me give by an example. Say error is increasing from one iteration to the next iteration. It will keep on increasing. Finally, you will get physically unrealistic solution. Okay, means it will blow up to
Yes.
some infinity or some negative infinity. So error should not propagate. But even if the solution is stable, solution may still be stable. Means you are going to some values, some convergence, still it may be physically unrealistic. Okay.
Yes.
Like for
Then both
example, so we have
not.
made some mistake in the discretization. We have made some mistake in the discretization of the sphere problem that I was telling. Iron sphere we have put in a furnace, and some mistake we have made, and our solution is giving that final temperature is minus 30 degrees centigrade. But it is converging to minus 30 degrees centigrade, not going to infinity or something. It is slowly converging to minus 30 degrees centigrade. Okay. So it is physically inconsistent, although solution is stable. Okay. So these are all different things. Okay. Good. So say if we have a rod held between 0 degree and 100 degree centigrade without any source term, initially it may be at some room temperature 30 degree. Okay. So the final steady state solution or any solution in between without any source has to be bounded by 0 degree and 100 degree centigrade, because boundary conditions are 0 degree and 100 and there is no source or sink term. There is no way that any point in the rod can go beyond 100 degree centigrade or below 0 degree centigrade. Okay, it cannot happen. So say if red line is the correct solution, steady state solution is a straight line going from 0 to 100 degree, right? And we are getting the green line from our discretization scheme after solving. Okay, this is physically realistic because our values are between 0 and 100 degree centigrade. So it is approximate because it is not accurate. It means there are some error. As you can see, there is deviation from the red line, but it is physically realistic. But consider this top blue line. Okay, at this the temperature is beyond 100 degree centigrade. Okay, however, it cannot exit 100 degree centigrade. So it is unrealistic. Similarly, this below blue line, at this point the temperature is below 0 degree centigrade. That cannot also occur. So it is physically unrealistic. Okay. So if your discretization gives this type of solution, we have to discard that because it is giving physically inconsistent solution. Okay. So the point here is that even if you have very coarse grid, say you are dividing the rod into 3 points, 3 contours, still the solution should be bounded between 0 and 100 without any source term. It cannot go beyond that. If I only take 2 grid points, still it should be there. That is the thing. Okay, it can be very inaccurate. Means it can be very large, means like this and then a step jump like this, but still it has to be consistent. Another example. Okay, 2-3 examples I am now giving to. One already we have discussed about the sphere. This is in one case. Flux has to be consistent. So say you have an insulated boundary condition. Okay. Insulated boundary condition means what? Adiabatic or insulated means that there is no heat flux at the boundary. Okay. So instead of constant temperature, you are putting insulated boundary condition in a wall. It means that dt dx equal to 0. Okay. K dt dx equal to 0 because there is no heat flux. So K is finite. So dt dx equal to 0. It means that just adjacent to the interface, T should not vary with X. Okay. Just adjacent to the interface, T should not vary with X because dt dx equal to 0. So the isotherms, the constant temperature lines just near to the interface should be perpendicular to the interface, okay, to the boundary. Just near to the boundary, the isotherm should be perpendicular, okay, because temperature cannot vary with X. So same temperatures will be at the along the X direction at the same height. Okay. So these red lines are the physically consistent solution. If we get a solution like this green line, okay, where the isotherms have some slope at the boundary, this solution is not physically consistent. Okay, it is an unrealistic solution. And this is a check that we always do. Whenever somebody shows me, one of my students, whenever he or she shows me a result. Sir, I have run some simulation. Can you check the result? First thing I check if there is a adiabatic boundary condition, whether the temperature profile at the interface is perpendicular or not. Okay, if there is no, if the temperature profile is not perpendicular at the interface adiabatic boundary, it means that something is wrong with the solution. Okay, so these are the checks that we have to do. Okay, yes.
Sir, at the
Tell me.
previous example, the rod is between 0 degrees Celsius and 100 degrees Celsius. So in between points, we will get temperature between 0 degree and 100 degree. This is a practical case, no, sir?
Yes.
But at case of insulation, there is nothing called perfect insulation. So if I get something little slope at the nearer boundary, will it be inconsistent?
Yes, it will be inconsistent because you are simulating the problem with perfect insulation. Okay, if you are
Okay, okay.
simulating, say you are assuming that there is some heat loss at the boundary, then you have to put that in the model. So you know that there is some leakage. Say you are doing an experimental setup and you are modeling it in CFD. You know that small amount of leakage is happening. Although you have put an insulating material, still then you have to put that heat flux, small heat flux at the boundary. So you have to put Q is equal to minus K dTdx at the boundary. Okay. So in that case, obviously there can be slope, but that slope is
So
correct because you have put some
simulation is
Q value. Yes. Tell me.
simulation is based on assumption what we take, so no, sir.
So if you assume that the interface is adiabatic in the simulation, it has to be perpendicular. Okay. Because you are
Okay,
assuming that
okay,
it is
sir.
adiabatic, then where from the heat flux is there at the boundary? It cannot be that. Already you assume that it is adiabatic. So in the simulation, there cannot be any heat flux at the boundary, right? Simulation is not experiment. That although you are assuming something, leakage is occurring. There is no way leakage can occur if you are assuming something because it's a mathematical problem, right? It's not a real
Yes,
life
sir. Yes,
problem.
sir. Yes, yes, sir.
Okay. So these are the sort of things you have to check. Say for example, there you have given no slip condition at the wall for velocity solution, and then see that there is velocity vector along the wall. Again, it means that physically inconsistent because you have given no slip condition at the wall at the final grid point near the wall, velocity has to be zero. So these are the things that you have to check. You have given zero shear stress condition. For some conditions, you have given zero shear stress condition at the wall. Zero shear stress mu del u del y equal to zero. Okay. Gradient of u with respect to y equal to zero. Then again the same thing, similar to this. The u velocities has to similar means near the boundary. Okay. It cannot change. So a lot of things are there. Okay. So this again I have written dTdx is equal to 0 for adiabatic isotherms have to be perpendicular to the wall adjacent to the boundary. This is one of the simplest problem that is given in assignments to check whether students understand this sort of whether they are getting correct solution or not. Okay, so you should be careful about this. So you understand. I hope you understand what is physical consistency. Okay, physical anything. It could have been for any problem. Okay, it should be what we expect from actual physics. Okay, but there can be a lot of error, but still it has to be within actual. Okay. Second thing is that overall balance. Overall balance means heat flux, mass flux, momentum flux, etc. should be balanced. Even if there is source term or negative source terms, like still they have to be balanced in the entire domain. And we have seen by our integral formulation that these terms are balanced within each control volume. And if we add up all the control volumes, they will get balanced. Only important thing to note here is that we have to be careful to calculate the correct flux at the control volume interface. Otherwise, the balance can get hampered. If the flux itself is different at the interface, like we have discussed today and in the previous class, then obviously balance will change. So if you take the correct flux, then automatically, so if you sum up, it will be balanced. Finite volume formulation inherently makes this possible. Okay, and the important point again here is that conservation should be valid for any number of grid points, even if it is a very coarse grid, even if we have only 2 grid points. Still, all the properties has to be balanced. Energy has to be balanced. Heat flux has to be balanced. Okay, that is the important thing. So these are the two important requirements of our discretization scheme. Okay. Let us take a break here, 5 minutes, and I will join after 5 minutes. Okay. If you have any questions, meanwhile you can think about it. So I'm back. I hope you can still hear me, students.
Yes, sir.
Yes.
Okay. Acha, what other faculty are doing in terms of showing the answer scripts to you, corrected answer scripts? How they are showing? Because online mode, how they are showing the answer scripts? Have anyone showed the answer scripts, corrected answer scripts to you guys
Not yet, sir.
for the midterm? Means I am not able to
No, sir.
come up with an idea how to what to do, means because I am not marking on the answer script also, and just I cannot give the soft copy also, means I am not supposed to give the soft copy to. So I will see what can be. Last time I just distributed the marks for the students in many cases, but uh, we are supposed to give when if I go one by one, then it will take huge amount of time. If I just keep on showing one, that can be done in other session apart of outside the class. That can be 5 minutes going through each of the students, but outside the class, we have to see what can be done. That is one of my concern, because I cannot directly. I'm not marking on the grade sheet. I'm putting the marks on some other Excel sheet. We have to see. Do you have access to that still to that like what is it, VBox, where you gave the exam? Can you still see your answer sheet, or you cannot see?
No, sir.
No, we can't.
It's gone after the exam, huh?
Yes, it's gone.
That access is gone after the exam.
Yes, sir.
So then there is no point in giving marks there also in VBox, because you cannot see. Some problem is also there in VBox, because everything was online. I was expecting to get the answer sheet as soon as possible after the exam, but they have taken more than 1 week to just send me the answer sheets. So I don't know what they're doing internally. Anyway,
Sir,
let
do
us
they
come back to
crop
this.
the answer sheets and then send to the professors?
It comes as a no.
So how
They give a login password ID. Okay, what I they give a login password ID. It's recording, so I don't want to go into too much details here. Okay, and using login and password, I can go and check each of the individual answers. Means say I go to your name. Who was asking question? Karthik, huh? Or
Yes,
somebody
sir.
was
Yes,
asking.
sir.
So I can see the roll numbers of the students. Then I click on your roll number, and there I can I see each of the questions and separate answers. Means if I click on one question, it will open a box and show me that answer only. It's like a long process, cumbersome process. Means click on one question, then that answer shows up for me. Then I click on another question, and again another answer shows up.
So does it happen somehow?
I can download the PDF also entirely. Yes.
So does it happen somehow you haven't received one particular answer, maybe because of some glitch? Does it happen?
Not really, not really. Every last time it was at least no problem, because one or two students who could not give the exam through this VBox, they had separately sent the PDF to me. Means not the students, the academic section has separately sent the PDF to me, exam center. This time also it has happened. One or two students could not give through VBox. I think for gas turbine, and they have sent the answer sheet to me. Or if you are unable to submit one answer and send it through email to them, they will send the answer separately to me. I can also download the PDF and check that. That is also possible, but that takes even more time to checking a PDF just by looking and. So let me see. Let me see. But last time there was no issue. Means while like it takes more time, but there were no missing answers, because the one or two answers were missing. I called the students to confirm. They said that no, they could not write the answer. Okay, I gave a chance last time. If they had missed also, so that they can send, but there were no issue. Anyway, let us come back to this. Remember, for this course, most probably lot of emphasis will be there based on the projects. Okay, already CFD students who have done CFD course as elective, they already know. Actually, you guys have done fantastic project last time. I tried to give good grades, but somehow the grades got reduced. Means initially I had given a lot of higher grades, but it was not allowed. So because there is some restriction in the number of grades, number of EX and A and all this. But based on the project, I was very impressed. Means most of this, means almost all the groups had done fantastic. So anyway, this time also the project may play an important role, because exams most should probably all of you will perform very well. So the main differentiation may come from project and somewhat from the and assignments also, which I will give. Okay, this time weightage of the project is also more. So let us continue. I don't want to discuss too much while recording is going on. So any questions from the previous part? How to discretize a simple, very simple problem using finite volume in 1D? At least you should be able to. And what do we mean by physical consistency and overall balance? Okay. Let us see some of the other important aspects. Okay. One is the how to treat interface conductivity, and second is how to treat the source term if the source term is not constant. Okay, these are the two things that are very important. Okay, if you look back at the equation that we have derived, where is our equation derived? This was our equation that we had derived, right? So TP, T and TW are anyway unknown, which has to be calculated, and we have assumed that AP, AE and AW and B are known. So it means that we already need to know the value of conductivity at the interface, all the distance values from the geometry and the B means how to treat the source term also we need to know. Okay, even if the source term is non-linear. So that's why to complete this analysis we want to see how K and S needs to be treated. So again, I am going to say that it's just a repetition of our CFD course because the syllabus is like that, and it is also important because these things are very fundamental of part of CFD. Otherwise, without knowing this, if you just run a simulation, most of the cases, 95% of the time you will get 5% of time you will get incorrect result, but you will not be able to find out why the incorrect result is coming. Okay, and this happens. In our cases, this happened a lot with my students because, say, for example, we solve a lot of problems where we have large difference in thermal conductivity, like energy storage problem where there is a metallic fin or metallic foam structure, and in between some phase change material, which is a very low thermal conductivity, and metal has very high thermal conductivity. So there is a sudden jump in thermal conductivity. So if you just means intuitively just calculate the interface thermal conductivity, as we will see, you will get wrong. Okay, so proper treatment is needed in those cases. But for most common cases, you will still correct solution intuitively also. Let us see what is the problem. Okay, so say the thermal conductivity is not constant in the domain. Okay, it depends on the position. So it does not depend on the time or temperature, but it depends on the location. Okay, for example, for the grid point P or control volume P, which goes from small w to small e, the shaded green region, this has a thermal conductivity Kp. Okay, say this is a material. Then the second part, second control volume, capital E, which goes from small e to the next interface, let us call this a small ee. Okay, has a different conductivity K capital E. Okay, say this is plastic. Okay, so one is aluminum, one is plastic. So our domain is a composite material, or say ceramic or something. Okay, ceramic metal composite, and we have drawn the control volumes in such a way so that the interface of the control volume falls at the interface of the ceramic and metal. Okay. Now the question is, we need to calculate this Ke dt dx, right? So Ke T minus Tp by delta x. T minus Tp by delta x is we have seen how it is. But what should be the value of K small e? Okay, what should be the value at the? I cannot just assume that it is equal to the aluminum conductivity or equal to the ceramic conductivity. So somehow I need to interpolate, and we don't know the variation within, because remember we are just storing the values only at the grid point. So our value of nearest value of conductivity is at point P, which is Kp, and nearest value of conductivity on this side is at point E, which is Ke. We don't know what is the variation even inside this domain also. Okay, I am assuming that it is constant, saying that this is aluminum, but need not be. Okay, so our nearest values are P and E, Kp and Ke, capital Kp and K capital P and K capital E. And based on these two values, we need to find out the K small e interface. Okay, and say these are distance parameter. On the east side, the face has a distance delta x e minus from grid point, not on the east side, sorry, on the west side, and on the east side, the face has a distance from the grid point of delta xc plus. Overall distance from P to E is delta xc, as we have shown here previously, standard notation, delta xc. Okay, so this part is delta xc minus, and this from here to here is delta xc plus. So we need to find the Ke or K equivalent at the interface E. What will be our gut feeling if I am a novice at this, or if I am just starting CFD solution, CFD calculation? The first thing that we always do is that we take an average. Okay, so here also we will take an average. Okay, if say delta xc minus is equal to delta xc plus, I will assume that K is equal to Kp plus K capital E divided by 2. Okay, if these two distances are equal, K is equal to K small e equal to Kp plus K by 2, linear average. Okay, or say arithmetic mean. In general, if these two distances are not equal, I will take a proportional. Like if this length is more, I will assume that it has more role. So delta xc minus into Kp plus delta xc plus into K divided by delta xc minus plus delta xc plus. Okay, linear average between P and E. Okay. So what will happen is that in most cases this is going to work. Okay, although it is not physically consistent, as we will see, it is not very accurate. In 95% of your problems, this is going to work. Okay, if you have a very fine mesh near a jump where there is some conductivity jump, still it is going to work. If there is no jump in conductivity, single material like air is flowing pipe, water is flowing through a pipe, like we do. Generally, sudden jumps are not there unless we are treating some composite material, heat transfer through a composite, like I was saying, metal fin PCM composite. Unless it's a composite material, in most cases this is going to work. Okay, but in those rare cases when you have a composite material where there is a sudden jump in conductivity or diffusivity, remember we are treating in terms of conductivity, but this discussion holds true for any other similar equation, like say chemical diffusion. So if there is a jump in diffusivity, like on one side you have pure air, on the other side there is a porous media. So there is a change in diffusivity from the air to the porous media. So there also same treatment needs to be done. Then this will cause problem. Okay, how this will cause problem? Let us see. Let us see what should be the actual thermal conductivity, average conductivity. Okay, based on assuming that this is a composite material. Okay, so from P to E is a single composite material. Based on the heat flux, we will calculate an average. Okay, so this P to E is a composite material going from grid point P to grid point E. Okay, average is a composite, and there is a heat flux Q double dash from the left side to the right side of the domain. Now heat flux at any cross section has to be equal, right? Because there is no source term. So heat flux at the pH grid point is also Q double dash, at the interface E also Q double dash, at the EH grid point also it is Q double dash. Okay. Now these distances, it has got blotted. Delta xc minus, delta xc plus, and the overall distance is delta xc. Okay. Say we have defined conductivity. On the left side of the material, composite material, we have Kp, and on the right side of E, we have Ke, K capital E. Okay. So for only the left side, I can write the heat flux as K dt minus K dt dx, right? Q double dash is equal to minus K dt dx. What is minus K dt dx? Minus K into T small e minus Tp. So minus is absorbed. So Tp minus Te, T small e into Kp, because that is the conductivity in this part, by delta Xc minus. Okay. So you can rearrange this in this form, Tp minus T small e by delta Xc minus by Kp. Similarly, on the right hand side, you can again write the heat T small e minus T capital E by delta Xc plus by K capital E. Okay. Where T small e is the interface temperature, which we do not know, okay, which is not part of the calculation. So this can be now, if you, this can be also written as, if you add this to numerator and denominator, this is written as Tp minus, this is equal to Tp minus Te, means capital P minus capital E, by delta Xc minus by Kp plus delta Xc plus by Ke. Okay. If you assume that there is a equivalent conductivity for the entire composite material, okay, if you do not distinguish between the, and say that the equivalent conductivity is K small e, okay, for the entire domain from here to here, it is K small e. I can also write the heat flux as T capital P minus T capital E by delta Xc, the entire distance, by K, based on the entire volume. This is the average value. So from these two equations, we get that delta Xc minus by Kp plus delta Xc plus by Ke is equal to delta Xc by K small e. Okay. This is the formulation for interface conductivity. Okay, this is the general formulation for interface conductivity in case delta Xc minus and delta Xc plus are not equal. This, instead of an arithmetic mean, this is the harmonic mean. So we see that in physical case, actual case, harmonic mean is a better physical representation of the interface conductivity. Okay, so if delta Xc minus is equal to delta Xc plus, so we know that delta Xc minus equal to delta Xc plus equal to half delta Xc. Okay, so just replace that, you have 1 by Kp plus 1 by K is equal to 2 by K small e. Okay, harmonic mean of K, or Ke can be represented as, means interface conductivity can be represented as 2 by 1 by Kp plus 1 by K. This is a much more accurate interpolation as compared to the linear interpolation that we have given here. Okay, much more accurate interpolation as compared to linear interpolation that we had given here, because we are seeing that this is what actually we obtain from physics. Let us try to understand this from an example. Okay, I have noted what I have discussed. I have already noted in the notes, so you can just go through the notes later on. Harmonic mean is a better approximation of interface conductivity Ke. Although linear mean can give correct results in most of the cases, in many cases it will give correct result. Extremely fine grids are required near an actual interface if there is a change in thermal conductivity, okay, which is not required for harmonic mean. And if there is a sudden jump, it may not even give correct result also, linear interpolation. Okay, but in most cases you will still get with linear interpolation, but in those rare cases you will get stuck and you will not know what is the error, why is the error happening. So it is better to always formulate based on harmonic mean, and it has happened with us. Means in real life we have done simulations where we are getting incorrect solution. Later I find that the student has linear averaging for the grid points interface. So let us consider an example. Okay. I will keep this open. So example is of a composite material where on one side you have a very high thermal conductivity material like say copper. Okay. On the right side you have a very poor thermal conductivity material like say some insulating material like wood is present. Okay, one side we have copper, other side. Okay. So what should be the expected heat flux if I put a temperature difference on one side, say 100 degree here and 0 degree on the other side? What should be the heat flux from this hot end to the cold end? This can be, you can assume that this is like a, say, what is it called? A ladle or a spoon, okay, with a wooden handle. Okay, one side of the spoon is on your bowl, which is heated, like you are cooking, and the metallic side is pan, frying pan, at a very high temperature, say 200 degrees centigrade. The other side you are holding in your hand, okay, and it is at your body temperature, 38, 36 degrees centigrade. What is the heat flux from this end to in this case? I am expecting an answer. Is it very high, moderate, very low?
Um, that depends on thermal conductivity, no, sir, of material.
Yes, so this, I am saying that this is a spoon.
Yes, sir.
Which has copper on one side, copper spoon, but it is insulated. On the other side, we have a wooden handle. Like
Flux should be
I don't know
nearly
whether you
zero.
know, like a ladle. Okay, ladle means, yes. So it's like a ladle or what is it called in English? I don't. Means you are using for frying. Okay. So you are able to hold that, right? You are able to hold that wooden spoon because it is
Yes,
a pressure
yes, sir.
cooker. You are able to hold the handle of the pressure cooker, although the pressure cooker is at more than 100 degrees centigrade, right? Because you have a insulating material on the handle of the pressure cooker. So it will be almost zero. Very small amount of heat flux will be there. Almost zero. Very small amount. So it means that physically the governing or controlling material here is the insulating material. Whether it is copper or aluminum or steel does not play much role if the other side has very high insulating material. Okay, if it is a aluminum pressure cooker or if it is a copper pressure cooker, it does not matter to me if I hold the handle. If the handle is of very poor thermal conductivity, I will still feel safe that the handle is not getting heated. Okay, although copper has much higher thermal conductivity as compared to aluminum, still I will not feel any, because copper or aluminum is not the governing factor here. The insulating material is the governing factor, and heat flux is almost equal to zero. So let us see what our arithmetic means gives us. Okay, so Kp is much larger than Ke. Okay, that example. Arithmetic means gives us that if the grid points are equidistant, average conductivity at the interface is Kp plus Ke by 2. Okay, Kp plus Ke by 2. If Ke tends to 0, it is almost equal to, if K is much less than Kp, it is almost equal to Kp by 2. Okay, if K is tends to 0, it is almost equal to Kp by 2. So is this correct? So we are getting a thermal conductivity which is half of that of copper if it is the copper on the left hand side. So it means that there will be huge heat flux from this 200 degrees centigrade to our hand temperature, right? But we see that actually that is not the case. So it is not correct. This average is totally wrong, right? This thermal conductivity average at the interface, the heat flux that is given at the interface will be totally wrong if we take this arithmetic mean, because it will give us a very high heat flux at the interface, which is dominated by the thermal conductivity of the high thermal conductivity material like copper or aluminum, and the thermal conductivity of the insulator is not playing any role in this case, much role. Okay, so this is totally wrong. Arithmetic mean. Okay, this is clear to you, to everyone? I assume it is clear.
Yes, sir.
What happens if we calculate harmonic mean? Harmonic mean equation was this: 2 by k is equal to 1 by k plus 1 by k capital E. 2 by k is equal to 1 by k plus 1 by k. 1 by kp can be considered to be negligible as compared to 1 by k, because kp is 1 by kp will be very small as compared to 1 by k. Okay, k is not 0, but it is very small value. Okay, so 2 by k small e is almost equal to 1 by k capital E, or k small e is equal to 2k capital E. Okay, here in this case, this thermal conductivity, average thermal conductivity at the interface is dominated by the thermal conductivity of the insulator, not of the high thermal conductivity material, which is our real life experience. We assume that the insulator should play the part in the thermal conductivity, not the material of the pressure cooker. So this gives us a physically consistent solution, this harmonic mean, because we see that if k is very small, the interface conductivity, average conductivity also should be very small. It means the heat flux also should be very small, and that is the case in real life. The heat flux is very small if we have insulator on one side of the composite material. Okay, only thing is that why this is 2 instead of k small equal to k capital E, it is because the way you are calculating the heat flux. Okay, when you are calculating the heat flux for this part is only equal to this
It is
distance,
2
means
because we taken insulation at half of the
half
portion.
delta x. Correct, correct. That's why it is coming. So you can just write
But
the equation in this form. So you have taken insulation at uh, half of the domain. So, but the actual length is twice that. Okay, so equivalent conduct 2 times of that, means you can just write the equation, you will find out. So, or let me just show based on here only. So if we just consider the heat flux here, the heat flux is the resistance, thermal resistance here is delta half delta xc. So if we consider that delta xc minus equal to delta xc plus, this is equal to half delta xc. So half delta xc by k capital E, the resistance here. The overall resistance in terms of the interface conductivity delta xc by k small e. Okay, so from these two also you can see that k small e is equal to 2k capital E. Okay, so harmonic mean gives us correct solution in this case also. Okay, so that's why we should try to take harmonic mean in most of these cases. So still we take linear mean, means arithmetic mean in many cases. But if a situation arises like this, where there is a composite material or sudden change in conductivity, drastically, like you have flow occurring and suddenly there is a fluid has a very low thermal conductivity, suddenly there is a metal block within the flow which is obstructing the flow. So although flow equations will be correct, but conduction has to be calculated within the fin also, or the block also, and then there will be a sudden jump in conductivity from the flow air. Say air is the fluid, from the air to the metal block, and that type of situation, this problem may come. Okay, in that type of situation, so we have to be very careful. Questions?
no, sir.
Okay, so we have only a little bit of material left for today. We'll finish it quickly. Okay, second is the treatment of the source term. Okay, which we'll continue to discuss in the next class also. But what I mean by treatment of this source term is that if there is a constant source term, there is no issue. Okay, we have seen already. Constant source term means we just put it as s, like after integration, it becomes s into delta x and come out as a coefficient b. Okay, which is independent of the temperature. Now there can be two other cases. The source term is a function. If it varies with space, then also it can be taken with some interpolation. Like we can assume that the source term is constant within each control volume, and again you will just put, for that control volume it will be s into delta x. For the other control volume it will be the other s into delta x. So there will be no issue. If the s varies with space, there is, you just assume that s is constant within a control volume. Okay. So there now the problem can come if s is a function of temperature. Okay. This is a special case, and this is an important case, because in real life many of these cases source term is some function of temperature. Okay, for example, source term at a place maybe due to some heat transfer. So you are solving a 2D problem, you are unable to take the third dimension into picture. Say I am solving the heat transfer over a wall. Okay, so wall is a 2D problem. I am solving it like a 2D problem, not across the wall, like over the wall. I am solving from one side of the wall to the other side. Okay, but there is some heat source that is coming. Say there is a solar from the outside, so some heat flux is coming on the wall, which is coming from a plane which we are not considering. Our XY plane is along the wall. Okay, I cannot show you, but say this is the wall. This paper is the wall. Okay, so this is our XY plane, and from within your screen, the heat flux is coming towards the screen. Okay, from the solar energy, and then there is some convective heat transfer from the outside of the wall to the wall. So from within the screen to the wall to the paper. Okay, here in this case. So in that case, these things are, because this is coming from the third dimension, which we are not taking into account, this has to be put as a source term in the problem to get accurate result. This cannot be put as boundary condition because there is no boundary there. So in those cases, the source term can become a function of temperature, because if the temperature changes, temperature of the wall changes, delta T also changes, so H into delta T also change. So means the heat flux changes. So the source term that we are putting will also change. Similarly, radioactive source term from the sun also will change. Okay. So source term can be a function of temperature. Okay. In actual physical cases. In many cases, I am just giving one example which have suddenly come to my mind. I have not thought of it previously, but there can be other cases you can think of. Source term, for example, chemical reaction source term can be a function of the amount of chemical that is present. So if more chemical is there, the reaction rate becomes faster or something like that, like in many cases, many of the cases. Okay. So again, there can be two cases. One is the source term is a linear function of temperature. If it is an energy equation, see again, although we are discussing in terms of temperature, all this discussion holds true for other equations, like say some convective diffusion, like not convective diffusion source term equation for chemical reaction, or some other type of equation similar to this. Okay, species equation. But this is the most common equation. That's why we are discussing with in terms of this. But same discussion holds true even for momentum equations with some exception. Okay, some of the non-linearity is extra, which we'll discuss later. So either it can be a linear function of t, or it can be a non-linear function of t. Non-linear means say it varies as t to the power 4, like in a radiation problem. Okay, linear can be it varies at t, like in a convection problem. Okay. So if it is a linear function, of what we need to do is that we need to divide this source term into two parts. One is the constant. Typically, this is called as SC. This is a standard notation. It is not my notation. It is used in the, and the second part, which is a function of temperature, because it's a linear function of temperature, I can write it as SPTP. So SC is the constant source term, constant part of the source term, and SP is the coefficient of the linear part of the source term. Okay, variable part of the source term for the pth grid point. Okay, if we do that, we can write our equation, same equation again. Look at this equation, it's the same equation. K dt dx east. This was from our previous, minus K dt dx west plus west to east. This part I had already written here, but this is actually west to east s dx. Okay, west to east s dx. So instead of s, now we will write sc plus spt dx. Okay, and for the pth control volume, this t is actually tp. I will come to this blue writing, whatever is written, but let us continue here. So this part we have already treated, Ke T minus Tp by delta X. We now know how to take Ke, the grid point values, minus Kw Tp minus Tw by delta XW. We know also how to take Kw. Delta Xc and delta XW we already know from geometry. Plus SC plus SPTP into delta X. Okay, assuming that SC and SPTP does not change within a control volume. Okay, SC and SPTP does not change within a control volume. We can just write this into delta X. Okay, so our equation will now be of this form. Exactly same form APTP equal to AET plus AWTW plus B. Same form. Only thing that is going to change is that coefficients. Okay. So coefficient of E is same. A is equal to K by delta. AW is equal to KW by delta XW. This SPTP delta X we will take to the side of the TP, other TP parameters. So what will happen is that if you take all the coefficients of TP common, you will get AE plus AW minus SP into delta X. Okay, this is the additional term that comes into picture. It was not present there. Okay, AE plus AW minus SP into delta X. This is the additional term. Okay, because of the linearity of the source term. And B is still same. It is S into delta X, but now it is SC into delta X, the constant part of the source term. So again, we have the same equation. So we can use our same solution technique for solving these equations. Once we know the coefficient, only thing that has changed is the value of the coefficient has changed. Once you calculate the value of the coefficient, you can use the same solver for calculating the actual value of temperature. Okay. Now what I have written here is also important. For this k dt dx, as we are discussing previously, if you remember in today's class at the beginning, that for different parameters we can take different profile assumption. What I have done here inherently is that for calculating the flux at the interface, we have taken a piecewise linear temperature between the grid points. This we have discussed in very much details. Okay. However, this temperature, this is also temperature. For this temperature, we have assumed that temperature is constant within the grid point. Okay. So it is not going like this and this. In the grid point, it is just equal to TP like this. So if I can open this, like it was suggested to me using this edge, right? Oh, not this one. Sorry. So we have two different profile assumptions. That is what I am trying to show here. Okay. These deep blue lines are the profile assumptions for calculating the source. Okay. And these light blue lines are the profile assumption for calculating the interface heat flux. Okay. That you can see that we have assumed that TP remains constant with the entire delta X. Okay. So as if from the west interface to the east interface, the entire temperature value. Similarly, we will do for the next grid point. Similarly, for the other grid point. Okay. It does not have any variation. So in this case, it is not physically inconsistent because we are calculating the source term. We are not calculating the flux at the interface for this. So if there is discontinuity here, that does not matter. We are only bothered with what is happening inside. Okay. For the flux, we are using a different profile assumption. So it is piecewise constant T profile for each CV. Okay. So what I mean is that we can take different profile assumptions as long as it is physically consistent. Okay. If there is no physical discrepancy, so what can cause physical discrepancy is this, like what could have been a cause of physical discrepancy if the whole balance would not have been correct. Means we are putting a source term, so there is some energy that is generated, like some heat is coming, right? So the total heat that comes in should be equal to the heat flux that is given in a given time. If our profile assumption does not capture that, then the total heat flux that is coming within a given time is not equal to the total energy that is numerically in the domain, then our profile assumption is incorrect. But this profile assumption will not be incorrect. It will give the correct solution. Okay. So there is no issue with this. Questions? One line is left. Let me finish. Then I will ask question. I will ask you for questions. So what if S is linear function of t? No issue. What if S is a non-linear function of t? Like S is equal to a plus b t to the power 4, like a radiation problem. In that case, also we have to use this formulation. S is equal to sc plus sptp. Okay, and the same equation, but this sp will now have some old time step value of t. Okay, this is known as linearization, as we will study in the. Our equation has to be linearized from the non-linear equation. So if the equation is t to the power, I can make it. If it is tp to the power 4, I can make it tp cube based on old time step value into tp based on new. So tp cube old into tp new. Okay, and the old values I will put. So only unknown is the single tp value, new value. Okay, so it has become like if it will become clear with some examples in the next class. Okay, this is known as linearization. We have to do source term linearization, and this sp will have non-linearity, and we will get similar sort of equation. Okay, however, it should lead to iterative solution because sp is not in one iteration, because you are assuming the old time step value, old iteration value for calculating. So you need a converse solution. So let us stop here. Any questions?
Sir, for this case, we are assuming source term as constant for that region. So
Yes.
we take profile like a single straight line. But if it is what you told as a variable of time, then how is the profile we have to take?
Variable of time or temperature? I am telling is variable temperature, not
Temperature.
time.
Yes, sir, temperature.
For that only. So if it is a variable of temperature, source term will vary with temperature, but the temperature profile means Tp also needs to be taken into account, right? Within the, like how Tp changes from small w to small e. So that Tp, that temperature, we are assuming that temperature is constant and equal to the grid point temperature. It is not linearly varying. Okay. Because of this only, I am writing this west to east Sc plus SC. West to east SC is constant. So what will be the value of west to east SC into west to east of dx? What is west to east of? It is the distance from west to east. So it is delta x. Okay. Now for the second term, west to east sp into t into dx. Okay. So let us take out sp. sp is taken out. Okay. So what is left is west to east t into dx. Okay. So you need some profile of t to calculate west to east t into dx. Okay. So if I take that t remains constant, I can take t out and it will become t into delta x. Okay. And that is what we are doing, t into delta x. So what is the constant? Constant t is equal to the t at the grid point. Okay. So I am assuming that t is not changing within the entire grid point. I am assuming that it is constant in the grid point. If t was changing linearly like this, then what will I do? I have to integrate actually properly. West to east t dx. Now I have to divide it into two parts. West to point P t dx, and now I know what is the slope of t with x. So I have to put that, and then from this P small e I have to calculate another integral. Okay. So to avoid that, I am assuming that t remains constant within the entire domain and is equal to the grid point t. Okay. This is physically constant. If you take the entire t in the domain to be equal to the grid point temperature, then your calculation will be correct. Okay. Is it clear or should I clarify again?
Yeah, yes, sir.
Okay, good. I will take the
Sir,
attendance. Okay.
we actually measure the properties at every grid point. We will take that.
Stored property. Yes, tell me.
When we are measuring the property at grid point, sir.
Yes. 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 When we are measuring the properties at the grid point, tell me. Cannot hear you.
But sir, someone is muting me, sir.
Why someone is muting you? What is your name? Suman, huh?
Yes, sir. As that time we take that all over the grid point only one temperature value we are measuring, na sir.
No, no. Can you repeat your question? I forgot what you are trying to say. Please
For
repeat
each
your question.
for each grid point for every sir again sir I will type sir question sir.
Type while I am taking attendance. Sai Dikshit.
Yes, sir.
Sai Dikshit.
Yes, sir. Yes,
You
sir.
are absent so many times. What is happening?
Sir,
I will
after
deregister you if it goes on like this.
no, sir. After
Last
midsum, it will not go
last
like this.
Friday you were absent. Be
Friday.
very careful.
Yes, sir. Yes, sir.
Okay. I
Yes,
will
sir.
not deregister, but the administration directly will deregister. They will not even call me also. Suddenly I will see that your name is not there. It will happen like that. So even I will not know that you will get deregistered.